Okay, I guess I can start recording. Okay, so till yesterday we studied about semi groups. Okay, so basically, what is that we are trying to do by studying semi groups? Say you have a linear differential equation x dot of t is equals to ax of t plus some b f of t. You solve this particular ODE and you get x of t equals x0 e power at plus integral 0 to t e power a times t minus tau b u of tau d tau. So semi groups basically, so here we were able to solve because a is a happy scalar that lives in R. But what if A is a matrix Rn cross n? How do you find your semi group then? What if A is a differential operator d square by dx square? How do you find exponential of that? So in order to generalize the exponent function, we study the semi group theory. So let's just recap what are the properties of semi group. First property is t of s plus s equals t of t into t of s, which is basically analogous to e power a times t plus s equals e power at into e power as. Next, t of 0 should be equals to identity. It is basically e power a times 0, which equals 1. And then you have your next PD next nothing, which is basically limit t tends to 0, norm of p of t times z minus z norm goes to 0 for all z belongs to z. This is basically e power at into some x minus x. Actually this goes to 0 as t goes to 0. So these are the properties of the semi group. So today we'll just try to explore on more properties of semi group, and then I'll be teaching about how do we get our A from the semi group, and some properties of A. With that, I think we can finish our basic structure of the solution of PD. Then we'll move on to the solution of PD. Maybe before that we might look into some properties of resolvent, but okay, that's fine. Okay, so I'll just give an example of semi group. So let us take a function f belonging to L2 0 1. So I have taught the definition of L2 0 1. Just recollect. L2 0 1 is basically all collection of functions such that their integral mod f square dx is less than plus infinity. So this is basically something called a Hilbert space. I'll explain more about Hilbert space in the second phase of our PD, where we are basically where we are discussing about distributions and so on, derivatives of distributions and so on. So basically there will be constructing what is called a Hilbert space and what is called a Sobolev space. So for now, so basically this is something that is a vector space. So what does that mean? If f and g belongs to L2 0 1, implies alpha f plus g should also belongs to L2 0 1. And also it is something called Banach space, that it means that it's complete. Say if there exists a sequence of square integrable functions converging to some f should also belong to L201. The proof of this particular thing that L201 is Banach is kind of robust, and in the sense that it is kind of tedious and beyond the scope of this particular course. So I'm just skipping for now. Just assume the fact that it's a vector space and it's a Banach space where all sequences is in L2 will converge to, if they converge to some limit, that limit also belongs to L2. Further, this particular space is equipped with an orthogonality property, that is inner product of f comma g, where f and g belongs to this space, is basically integral 0 to 1 f of sigma g of sigma d sigma. The fact that our functions have an inner product, it means that this is an Hilbert space. So a Hilbert space is something that is a vector space, which is a Banach space, and if there is a notion of inner product, then it is called an Hilbert space. So this is a hand-waving way of understanding things. Okay. For us, the main thing is to understand these spaces and to apply our optimization algorithms later. Okay. So one example of a semigroup is this. T of t is AT. A being a scalar, a simple semigroup. So T of t, if A is a matrix, e power AT, which is equals to 1 plus AT plus a square t square by 2 factorial plus so on to infinity. This is basically an example of semigroup, and I will just give one non-trivial example. So this is something that is related to our heat equation in our PDEs. T of z equals sigma n is equals to 1 to infinity e power minus n pi whole square t times z comma phi I into phi I. Okay, wow. Where did this big expression come from? Here, phi I is basically sine n pi x. So if you look at this particular thing closely, this is solution of heat equation with Dirichlet boundary conditions. You basically solve this particular PD, dou u by dou t is equals to dou square u by dou x square, with u of 0 comma t equals u of 1 comma t, which is 0, and u naught of x is u of x comma 0, and you just plug in your u naught here. What you get is the solution of the heat equation. And this particular inner product is, as I have defined before, integral of z phi I dx. So this is a semigroup. So now you understand how we are generalizing the notion of e power at. So basically, if you take e power dou square by dou x square of t, you end up with this expression. Okay. Just increase the font. So I'll just show how that magic happens in a meanwhile. I'll just show. Okay. So now we'll go to properties of semigroup. First property is norm is basically operator norm. Norm of T of t is bounded. Is bounded on every finite subinterval of 0 to infinity. this one property. So basically proof requires something called uniform boundedness principle. So a kind of mathematically robust. So let me omit the proof of this. I don't want to burden. So so basically norm of T of t can be basically less than or equals to m e power omega t, where this is something that we can do. And b, dt is strongly continuous. So proof of the semigroup being strongly continuous is basically you just take norm of T of t plus s into z minus norm of T of t into z, which is basically less than or equals to norm of T of t into a norm of T of s z minus z. So by the strong continuity property of the semigroup, this goes to 0 implies this goes to 0. So now another property is limit t tends to 0 plus 1 by t integral 0 to t of sigma goes to z soil. For that you basically take this particular expression 1 by t integral 0 to t norm of sigma z t sigma minus z norm, which is equals to norm of 1 by t integral 0 to t of sigma z minus z d sigma, which is less than or equals to 1 by t integral 0 to t norm of t of sigma z minus z d sigma. So now, as by the strong continuity property, this becomes very small and this goes to 0. I'll just give one identity. I have written the proof in notes. I don't think that's that required. So basically, take this omega naught equals limit t tends to infinity 1 by t norm of t of t implies this is a limit. So basically our norm, this is upper bound. How to get an upper bound for our semigroup? Yeah. So this is an identity. So now the main question is, how do we link the semigroup to our PDE? How do we get our A operator? So say you have e power a p. So what are the ways of getting a? One thing that you can do is differentiate e power a t and take limit t equals 0. So that is the basic idea of things. So you have so we define this is an infinitesimal generator of a C0 semigroup. It's just a term. So we basically get our operator A from e power at by this particular limit. Limit t goes to 0 plus of t of z minus z by t, where domain of A is all such z in z such that the limit exists. So wherever you have this particular limit, for the values for z for which this particular limit has a finite value, is basically in the domain of z, and your operator A is obtained from that. So let me show how do we get double derivative from the semigroup. So say you have the PDE dou u by dou t equals dou square u by dou x square. In notes I have given Neumann boundary conditions, but here I'll just take Dirichlet boundary conditions first. Not for simplicity, it's just that we'll have two examples. Some initial conditions. So what's our trick? We do variable separation method. 1 by t dash 1 by f into f double dash implies which we equate to minus lambda square, implies f is equals to c1 cos lambda x plus c2 sin lambda x. So you just plug in this Dirichlet boundary conditions, you get your f to be cn sin n pi x, and the solution of, once you plug it in your t and solve the ODE for t, you get u of x comma t equals sigma n is equals to 1 to infinity e power minus n square pi square t into some cn times sin n pi x. So what's your cn? Cn is equals to, you keep t is equals to 0 and then 1 by integral sin square n pi x from the limits 0 to 1 dx into integral 0 to 1 u of x comma 0 sin n pi x dx. So this is the value of your cn. This you can say I define sin n pi x to be some phi, which is phi n. Then this is some inner product on this, so I can write cn as basically phi n comma u0 of x divided by, I think the value of integral 0 to 1 sin n square pi is 1 by 2. So cn is basically 2 times phi n by u0 of x. You can basically remove this 2 by defining your phi n to be root 2 sin x. If you take root 2 sin x, things will get cancelled and you will just get this particular expression. Your cn will be phi n times integral of phi n u0 of x dx. So finally, the solution of this particular PD, I'll just simplify and write the solution of PD once. So the solution of the PD is u of x comma t equals sigma n is equals to 1 to infinity e power minus n pi whole square t into u0 into phi n into phi n. So now I define my action of semigroup t of t on some initial condition u0 to be sigma n is equals to 1 to infinity e power minus n pi whole square t into u0 phi n of t. So now just see how am I connecting the solution of the PDE to the semigroup. Now how do I get my operator A from this? So if I differentiate this particular expression and put t is equals to 0, I must get my operator A, which is nothing but dou square by dou x square, right? So this is basically x dot into this dou square by dou x square into u, right? So now let us differentiate and equate this to 0. What you will be getting is A times u0 equals sigma n is equals to 1 to infinity e power minus n pi whole square into 0 into minus n pi whole square. Although I am just differentiating this kind of carelessly right now, you need far more rigorous, robust mathematical theorems on differentiation under this infinite sign and everything and so on, which we basically covered in our real analysis and stuff. I'm just kind of trying to avoid that mathematical abstractness for now. So you get this. So your operator A, I'm just simplifying them. So your AU naught becomes sigma n is equals to 1 to infinity minus n pi whole square into u0 phi n into phi n. So this is basically the representation of double derivative operator as an infinite sum. So you can write your double derivative operator as a sum of infinite functions. So your I'll just show. Just erase that. So this is like a magical moment. Okay, if you don't appreciate it, it's fine. So basically your dou square by dou x square of u equals sigma n is equals to 1. Just a second. So dou square u by dou x square is equals to sum of minus n pi whole square times u comma phi n comma phi n, where phi n is basically sin n pi x. So this is how you get your operator, and this is basically A times C, where A is the double derivative operator. That's how you land up with things. So that's how you connect with A and the semi group and so on. Okay, now we'll just try to understand the properties of A. So property 1. If Z0 belongs to domain of A, that is limit of the fraction of the semigroup into Z by T. Just recall. implies T of t into z naught also belongs to domain of A. So what this basically physically means, say you have something, this is domain of, this is a space, this is space. So this is your Hilbert space Z, and this is the domain of A. Say if your initial condition is in domain of A, it means that your entire trajectory of solutions is in domain of A. So in your optimization algorithms, so you can basically minimize the search effort. I mean, if you are finding the solution of PD, you will have some additional constraints, and your search space will be reduced to domain of A. So that will get on to later on. That's basically optimization on Sobolev spaces. So, okay. The answer is, so you just take this T of t plus s minus T of t by s z equals T of t into T of s minus by s into z naught, which is equals to T of s minus 1 by s into T of t z naught. So because this is a z naught, this exists and this exists, hence I mean this A times this. So this exists, hence this will exist, hence T of t z naught belongs to domain of A. And obviously so next property that we'll go to is so today I'll be finishing the basic concept of the infinitesimal generator and the properties of semigroup. Tomorrow I'll just talk about something about resolvents, and then let's end. Then I'll talk about the nature of solutions of PDEs, and then I think we can end the concept of PDEs. Next, property B, d by dt of this is something that you expect, right? You just divide d by dt of e power at, e power at being a semigroup, you say e power at or e at power a. So this is what we'll get. So this basically comes from the fundamental definition of limits. T of t z naught equals T of t plus s z naught minus T of t z naught by s. S goes to 0, which is equals to T of t into T of s minus 1 minus identity into z naught, which is equals to T of s minus 1 by s into T of t z naught. So take your s to be small, what you get is T of t a z naught equals a times T of t z naught. This is definition of A, and you do this inductively. So z naught obviously has to belong to domain of A for this thing. So you just do this inductively, and what you end up is d by dt power n of T of t z naught is equals to a power n T of t z naught, which is equals to T of t into a power n z naught. But here z naught obviously has to belong to domain of A, or else the limit won't make any sense. Okay. Now I'll just give an identity directly. P of t into z dt from the 0 to capital T belongs to domain of A, and the value of the integral 0 to t z of dz dt equals P of capital T z minus z. So this is an identity. There are some properties of semigroups which we may actually want to know to understand the solution of PD. And next question that we have is domain of A is dense in Z. So what does this mean? What does density mean? So this is something that I have told vaguely in real analysis. Say you have a set of real numbers. I will say that the rationals are dense in R. So what does that mean? So basically, if x belongs to R, there exists a sequence of xn in your rational number such that xn goes to x as n tends to infinity. So any real number can be approximated with accuracy that you desire by rational numbers. See, obviously, right, say you have pi. It's a basically irrational number, so it's not a rational number, but it's a real number. You can basically approximate it to arbitrarily small value as 3.14 something. So you can get a 10 power minus 100. So you can approximate it with any arbitrarily epsilon that you want. So similarly, all the elements in domain of A can approximate any element in the overlying Hilbert space. Okay, so this is something I'll just state as a property. And another property is A is a closed operator. What does closed operator mean? So if xn is a sequence in domain of A such that xn converges to some x and this is in Z, this should imply that A xn, if it converges to y in Z, y should be Ax and x should belong to domain of A. This is the definition of a closed operator. So I guess with this we have completed the basic math behind the semigroup and the infinite SML generator, which is basically analogous to e power at and your A in your abstract differential equation. I guess tomorrow we'll talk about resolvent operator, and after that we can go to solution of the PD. Okay, with that I'll end today's class.